All right, let's start. And I think maybe the most important thing to do right now is to review this second exercise here. So I want to talk to you about how to analyze these problems. These are the problems that will appear on exam 1. So I want everybody to be very clear about how to do these problems. The other problems you need to work on are the lab exercises. Those are very good. Those are better for your future. They help you learn what you need to learn to be successful as a computer scientist, software engineer, to work in the software industry, as a mathematician or whatever. There's a lot of people have to do programming these days. So the lab exercises are all about learning programming skills. And they're related to what is asked on the exams as well. But in an exam, I can't ask you a long, involved software engineering problem. The questions are shorter and they're simpler. So these are the kind of problems that you'll have on the exam. Let's go over these problems. I'm just going to work inside this. Here's just a shell here of a program. Just says OK. Here, it says OK, good, we got that. So I might want to test my code here. Like this. What does this code print? Now on the exam, you don't have access to a computer. You have to think about this problem and understand it. Put that one right there. What is this, when that code runs, what does it produce? Did I talk about this already? Am I doing the right thing? I just want to check. Am I headed in the right direction here? If you're thinking about or worried about something else, I'll do that. So you can steer me where we need to go. This makes sense, right? Okay. All right. So, and I'm going to tell you. Here's a problem that some people are having, by the way. When you copy this text and paste it into the editor, you may get compilation errors that you can't figure out. And the reason is that the PDF document is using a character set that's different than what the compiler can process. So in the character set that the PDF document has, this semicolon is represented by a binary value, a number value that's different than what the compiler is looking for semicolon. So you can represent a semicolon with different kinds of numbers. It depends on the character set you're using. And it's my mistake. I keep making a mental note. I need to make a note that on this, in this exercise, I need to alert people. In this exercise, I need to alert people about copying and pasting out of the PDF documents because there's a problem with that. And I keep forgetting to do that, but I'll try to remember today. I'm going to add a note here, although it's on the late side now. But when you go to look at these exams here from the past, you'll have the same problem. So don't copy and paste out of the PDF document. Just type it in manually. And I'll illustrate, in case you don't understand what I'm talking about, I'll illustrate that right now. If in fact it gives me a problem, I don't know if it will. So the problem here is, you see the indentation? I just fixed the indentation, right? So I'm inside main. This is an opening brace right there up in the top, and the closing brace is down at the bottom, down here. Here's the closing brace, the opening brace. So all the statements that are inside there, they're inside this function that's called main. The main is the function that gets invoked, or it's the entry point of the program. It's where execution starts. Later, we'll be defining our own functions. So main will call other functions, and we'll get to use functions as a way to organize our logic, our code. But for the time being, we're just going to work in the main function by itself. So whenever you have a block of statements like this, statements that are inside an opening brace and a closing brace, whenever you have that block, you want to indent. Not because the compiler wants to, but because the people that are reading the code need to see that. Otherwise, it's too hard to read the code. So this is a statement 1 right here. This has an indent relative to the main function. This is the second statement is right here. The second statement is a complex statement, a compound statement. I've highlighted it right there. It has substatements in it. The substatements are indented relative to their parent, the while statement. So that's why you get a double indent here. It's not a single indent, because this line here is inside the while loop. It's not a direct child of the main function. It's like a grandchild of the main function. So it's 2 levels away from the main function. So you show it that relationship with 2 indents. Same with this one. And this closes, see the editor, I put my cursor down here on that brace, and the editor highlights the other brace just to show us, where that block starts and ends. But this is very important. So you must use indentation properly when you submit code in this class. Right? It's very important. Now let's see if this code, when I look at it, it just looks perfect. It should compile. Let's see if it does. Maybe it will compile. See, it does not compile. Look at that. Non-ASCII characters are not allowed outside of literals and identifiers. So and it has a marker here on the semicolon. You see that? Int I equals 0. It's saying that's a non-ASCII character. This one right here. That one. It's complaining about that. Look, see that? Int I equals 0. That's the first error. Now if I take that out, all right, and then I put one back in again, it looks like the same thing, doesn't it? But it's different. The underlying numerical representation of that semicolon is different now. Now it is an ASCII character. Now watch this. I'm going to run this again, and this error message here, there's 2 lines talking about that are pointing to the semicolon. This will go away, and the first error that will appear will be this problem with the semicolon in that line, the C outline. Ready? Did I save this? Make sure I saved that. You see that? The first error is that C outline. So I fixed the problem. I deleted a semicolon and added it back in again. So look, you didn't see it. See, this is an example of a bug. Did anyone figure this out on their own? Figured it out on your own? You guys figured it out on your own?
I cut and pasted it and had an issue and then just wrote it in myself and fixed it.
You fixed it. Did you understand what was going on?
Nope. I saw the issue, but I wouldn't have known that.
A lot of times when you're working on these computer problems, you'll fix it and it'll work. But I gotta tell you, it's bad to it's okay. I mean, when you're under a deadline and the boss you want to go home and eat dinner, you're gonna fix stuff and move on. But in the long run, you've got to push yourself to try to understand why did the fix work and what was wrong to begin with. And I'm telling you what was going on there, okay? So that's just it's a mental habit. You want to try to understand how things get fixed. If you're just tinkering and playing with things and, oh, it works now, okay, I'm not going to touch it anymore. That's not going to get you very far. It might get you home, in time for dinner, but that's about it. You're not going to, next time the problem is going to get worse and, you'll get more delayed, and you're not building your knowledge. So you really do have to dig and try to understand what's going on. But sometimes it's just beyond your ability. I mean, you know, I can't. I fix stuff that I don't understand. What do I do? What's the main fixes? Probably my main fix is your main fix as well, right? When you're having trouble on your computer, what do you do?
Turn it off and turn it on.
That's it right there. You reboot. That's it. How many problems you fix by rebooting? And we're talking, the system's ridiculously complicated. The operating system's got, what, Windows has 10 million lines of code in it, you know, and plus all the applications running on it. I mean, it's incredibly complicated. If you say, oh, I'm not gonna just fix it because I got to understand it first. Well, you're never going to understand 10 million lines of code. That's not even open source. I mean, it's hidden. You know, if it was open source, like say Linux or BSD behind a Mac, you still have the problem of reading through all that code and figuring out what happened. And I mean, it's beyond your ability. Anyway, that's getting off on a tangent here. Let's look at this code here. We need to understand how to analyze this just manually by thinking about it and coming up with an answer as if we were in an exam. And then we'll check our answer by running the code here. So here we're declaring a variable I. And then that's the first thing we do. We initialize it to 0. And then we enter this loop. And the loop condition is that I is less than 7. So whenever I is less than 7, the loop condition is true. And we execute the block of statements that are the child statements of this while loop. So initially I is 0. So we're going to run these two statements. And after we run these two statements, then we check the condition again. Now the statements that run inside the while loop should have some effect on the condition. So you can see here we're incrementing I. That's why eventually I will get big enough, it'll hit 7, and the loop condition will be false. That's when we finish the loop statement. After the loop statement is done, we do the next statement, and that's this statement. So there's 3 statements. This program is comprised of 3 top-level statements. This is the first statement. The while loop is the second statement. This output statement is the third statement. We've got substatements. So I'm just talking about the top level in the hierarchy. That's the first level indent. We've got 3 statements. One of the statements has substatements. Well, I'm not counting those right now. Well, we could if we wanted to. All right, so let's just walk through it. So I is 0. 0 is less than 7. Let's print something. And we've got we have two operations, so an output operation and multiplication. Now, this multiplication has higher precedence. In other words, it runs first. We do the multiplication first before we do the output operation. Now, so we need to evaluate this expression right there, 2 times I. This 2 times I, when that expression completes, when it runs and executes, does it modify I? No. This does not modify I. It produces a value. It reads from I. What I have highlighted there is an expression that reads from I. It uses I. It does not otherwise modify I. It doesn't touch I in any other way. It does not modify I. So we take 2 times 0, we get a 0. So we're going to see out 0. So we output a 0. And then we increment I. When I is currently 0, so now I will become 1. Now, we've just completed, after incrementing I, to go from 0 to 1, we've completed executing the loop statements. So now we check the loop condition. Is I less than 7? Well, yeah, I is 0. You know what, just to keep track of it, I'm going to get lost here. So we started with I equal 0, and we incremented I, so now it's 1. So now we need to do this statement. 2 times I is 2 times 1. That's 2. It doesn't change I. We just get 2 here. 2, this expression evaluates to 2. It is the right hand side. It's the right hand side. It's the right side operator of this output operation. Operand, rather. So we output 2. I put a space in there. It doesn't actually output a space in the code. I want to put it in there anyway, just to make it more readable. Then we increment I. So now I becomes 2. After we increment I, we're at the bottom of the loop. So we go back and check the loop condition. The loop condition, I less than 7, is still true. So we continue executing the body of the loop. So 2 times I is 2 times 2. That's 4. We output 4. Now you can see what's going on there, right? It's outputting, it's incrementing I, and then it outputs 2 times that. It's going to do like, if it kept going forever, it would do that, right? So, well, it's not going to go forever. It's going to stop. For what value of I does the loop stop at? It stops at 6? I would, I wouldn't say it like that. I mean, maybe that's right in your thinking. It stops at, does I become 7?
Yes.
I become 7. Does I become 8? Huh? No, I does not become 8. The last value that I takes on is 7. When I takes on the value 7, it does it at the bottom of the loop. And then the loop condition fails. So that's it. We don't output 2 times 7. We don't output 14. We must have outputted 12. So 6 is the last value that I took on for which the body of the loop ran. When I became 7, it stopped. So that's the answer on the exam, 0, 2, 4, 6, 8, 10, 12, right? But now let's test it. Oh, of course, we have to fix our code here. I need to replace all those broken semicolons. There may be other problems, like that quote. This quote might be wrong, for instance. Let's see. No, it seemed to work. There, and I even have the OK. So it's 0, 2, 4, 6, 8, 10, 12. Like I said, there was no space there. I could have, see on the exam, I don't want to make it too confusing, but if I did that, then we would get a space. We could get rid of this OK as well. It's easier to look at because there's no new line there. But that's how you do that one. What about this one? Rewrite the code in figure 2 so that it uses a while loop rather than a for loop to accomplish the same output. So here it is with the bad characters in it. I'll try to get this to work by taking the semicolons out. So we want to rewrite this a loop. We want to rewrite this as a while loop. The while loop has some kind of initialization here. Then it says while, some condition. And then it has the, the body of the loop, the statements. See, that's compressed in here. This is the end of the loop. These are the statements of the for loop are between those braces. That's these statements. But in the while loop, you also contain this end of loop operation, unless you don't need it. The condition is the same. I less than 7. That's what the condition is. And initialization, well, that's here. Oh, look at that. I can use that word. So this is, this is just as this. I'm going to tell you, this is equivalent to this. That will work exactly the same. You can have an empty um, spot, and you can have an empty expression in the for loop. And we just put the condition out here. I mean the initialization code out here. You know, it's although you can do that, people don't do that. This is what it's designed to look like. In the while loop, you have to have that initialization code done first separately from the while statement. So the statements are, you know, cout 2 times I, and what goes here? Increment I. Yeah. That's the end of loop operation up here, see? This is the thing you do at the end of the statements inside the loop. So this is the answer. The answer on the exam or in this homework assignment would be that. Let's check. We got to make sure that really works. So I wrote it like this. Make sure that it really works. Let's separate things out. You see how I'm doing the line spacing? I'm just making things really neat. Maybe I'll do it like that. You know, this is kind of arbitrary. I mean, you could do it like this too, right? Whatever you like. Line spacing is more variable than indentation is easier to, I mean, it's not as flexible. You know, you've got to indent in certain ways. All right, let's see if they produce the same thing. They do. Oh, that's that. Oh, wait a minute. Oh, there's the answer right up there, isn't it? Did anyone notice that? Yeah, okay. So number 3, how many times does the body of the for loop run in the code in figure 3? How many times do we print I? Don't actually show the I's that get printed. Just how many times does that, those statements, does that one statement run? This is not a statement, this is a comment, this is ignored by the compiler. It's discarded. When we generate the machine instructions, the comment has no effect at all on the resulting machine instructions. But this is, this has a result. This is translated into machine code, which has some effect that runs at a runtime. So how many times does this run? 100, right? See, you start at 0. When I is 0, and k here, k is 100, k doesn't change. The body of this loop does not modify k. So this limit point here, k, is always 100. So you can just forget about k and say that's 100. So, and this statement doesn't modify I. The only place that I changes is here, which is the end of the loop. So I starts at 0, the loop runs, I goes to 2, the loop runs, I goes to 99, the loop runs, I goes to 100, the loop does not run, because 100 is not less than 100. That's false. So we do not do the loop. So we do the loop when I is 0, 1, 2, all the way up to 99. How many values is that? That's 100 values. If it was 1 to 99, it would be 99 values, but it's 0 to 99. It's 100 values. I'm trying to get you used to this counting method where you start at 0 and you show the end with a strictly less than operation. It's just the style. That's how programmers tend to do it. They don't all do that, but I would say 99% of the code out there, more than 99% of the code that has a loop that looks like this, is going to look like this. 99%, at least. So I just want you to get used to that. rather than getting used to a simpler, probably a simpler expression that won't serve you in the long run. All right. So the answer to that one is 100. Any questions? Before we run out of time, I want to just check something here. Today is, what is today? 12. So we're like up to here, this algorithms lab. Oh, we started talking about this, didn't we, or not? We didn't do this yet. Oh yeah, detecting prime numbers. We did this, right? Prime numbers, okay. Factoring, generating random colors. All right, so we got to get to those two. And then on Wednesday, we're going to talk about functions. And then a week from today, we'll have that exam. So let's get ready for the exam. All right, let's keep working on these. How many times? Oh, no, that's not right. When the code in figure 4 runs, what does it output to the console? All right, let's look at that. Oh, got that wrong. There we go. I got it right now. Get rid of the semicolons. Some compilers don't handle the spaces in PDF documents sometimes. It's just replacing the semicolons isn't always going to work for you here, but it seems to be working right now. I've seen problems with spaces not being handled correctly. So I advise against this process. Did I do this one? I don't know. So how do we analyze this loop here? The first thing to notice is, do you see the body of the loop? All it does is change the value of I, which influences the loop condition. It doesn't output anything. When the while loop completes, then we come to this output statement. So we're going to print one number, that's it. We're not printing many numbers. You might want to keep track of many numbers, but you're not printing many numbers. So your answer shouldn't show that you're printing many numbers here. You're only printing one number. So I starts at 11, and we keep adding 3 to it. We keep adding 3 to I. We start at 11, we keep adding 3. So 11 to 14 to 17 to 20 to 23. We do that until I becomes what? Well, when I is 99, we still add 3, don't we? So when I becomes some unknown value bigger than 99, I don't know, is it going to hit 100 or 101 or 102? It's going to hit one of those. I don't know which one it hits, because we're starting at 11. That's an odd number to start at. So look at this. We're going to, the I, think about the values that I takes on. When I is done here, I is going to be the original value of 11 plus some unknown n number of 3s. So each time we run the loop, we add another 3. So we're adding n 3s. So that's what I looks like when we finish the loop. Now, the I we print here is the I that makes the loop condition false. It's not the last I that made the loop condition true. It's the value of I at the end when the loop condition is false. So we just have to solve for n here. When does this, for what value of n, what's the smallest value of n that makes that expression greater than 99? Well, let's think of it like this. How about if we do this? I'll try doing it a new way here. maybe we want to look at, here we're comparing, we're looking for a value of n, the smallest value of n that makes this true. Well, why not solve this problem? What's the smallest value of n that makes this true? What's a good value for n there? Anyone let me know. Let's say n is 20. Let's suppose that n is 30, right? Then that's, if there's 33s, that's 90. Well, that's one too many. So it must be 29 threes. N is 29. So n should be 29, right? So, so 29 times 3 is what? Check me, make sure I get this right. I think that's 87. And then, 11 plus 29 threes is going to be 98. So I hits 98. Let's check our math here. I also hits 98 minus 3. So it hits 95, right? I hits 95. And when I hits 95, oh, this is true. I see I is true when it's 98. So it has to go 30 times. So we're going to hit, I is going to hit, when I hits 98 plus 3, that's when the loop condition is false. So it's going to hit 101. I feel like I'm confusing people. Sorry. I'm trying to make it simple. Do you get this? It's all right? You're not going to get it unless you struggle with it. If you just listen to me, you're not ready for the test, okay? You got to think it out yourself. And this, I just presented, I'm just trying to think out loud to show you, how I did it. And there's other ways of doing it. Let me show you another way to do it. Let me show you. This is the way, and I've done it so many different ways. This problem, because every quarter I use the same problem. I say, well, what is I? I know I got this. It's 11 plus 3 times something. That's the problem right there. So, we're going to add some unknown number of 3's. And we want to know how many we're going to add until the loop condition becomes false. Well, just try stuff. I'll try 30. Actually, that's what I did try, isn't it? And I got 90 plus 11, which is 101. I said, well, that makes the loop condition false. Maybe I tried too many. Well, let me try 29 threes. Well, let me just take 1 3 off of this. That's 98. 98 makes the loop condition true. So it couldn't have stopped at 98. It must have stopped at 101. I'm going to print 101. That's easier, that reasoning? That's faster to the point, right? Okay, so just do some guessing. I think that's how I normally do it. That's how I normally do this problem. But I have seen students in the past, they like the formula. Oh, I see, you're going to solve the equation. And so you can do it that way as well. So 101 is our answer. Let's see if we got it. 101. All right. Let's look at the next one here. All right, that's a semicolon, and that's good. All right, so we have 3 output operations. Which one do we do first? The one on the left. I mean, of the three output operations, we do that. This output operation before this output operation. But of course, we do the division before any of the output operations. That has higher precedence. So what's 1 divided by 2? 0. Good. 1 divided by 2 happens to be 0 because we didn't say integer divided by or floating point divided by. But we should have thought that. When I look at this, I say integer division in my mind. But when I say it out loud in a lecture, I'm just saying divided by. So I'm lying, actually. This is not divided by. This is integer division. And then we print a comma. And then we do floating point division, 1 divided by 2. So one of the operands is a floating point value. So that means it's floating point division. That's going to be 0.5. And that's what we're going to get. There we go. So that one's pretty straightforward. What about this one? This is the one that you can listen to me over and over again in lecture. But if you don't try to think this out yourself, you're never going to get it on your own in an exam, I'll tell you that. So you got to think this one out. And the trick is this pre-increment operation and post-increment operation. That's what I'm trying to get you to understand what those are. You see them in practice. You see that stuff. You got to know how to understand it, what it means, what it does. Initialize I to 2. All right, I is initialized to 2. Oh, here we've got a k. K is going to be set to something. All right, what does k get set to? Oh, that's post-increment, right? So we have to read from I first before we change its value. The increment is post, it's afterwards. So let's go ahead and read the I. I is 2. Multiply by 2, we get 4. Assign 4 to k. Oh, let's not forget, it's now post. Let's increment I. I is 3. After 4 gets assigned to k. Got it? Everyone get that? If you're just listening to me, it's not going to work. You got to sort of practice that thought pattern, on your own. All right, so let's do the last line here. Oh, that's pre-increment. That's a lot simpler, okay? It just means increment I. And that's the first thing you do. It has very high precedence level. It's going to run first. So we're going to increment I. I becomes 4. All right, now we forget about that increment altogether. Just drop it. Now we read from I and multiply by 2. Are we modifying I when we multiply by 2? No, we're not modifying I. This increment, this modifies I. This is an expression that results in 4. It also sets I to 4. That's different than this multiplication here. It's an expression that evaluates to 8, but it doesn't modify any variable. It's just an expression that becomes 8. This is an expression that becomes 4, but it also modifies I. See the difference? It does more in a sense. It's an assignment and it's an expression that evaluates to some value that's used in another expression, a parent expression. All right, so then this is 8. I is 4. 4 times 2 is 8. And then we're going to add k. K is 4, so that's 12. We're going to see out 12. So always a small chance I get this wrong up here. I got to be pretty careful, right? I'm pretty sure it's 12. There we go. Any questions on how that works? All right, that one's done. Write a C++ program that computes the sum of integers 0 through n, where n is an integer entered by the user. Compute the sum of integers 0 through n. This is your starting algorithm. This is an algorithm. It's a sequence of instructions that produce some result, some information output. So we want to basically, we want to print, or we want to compute, what was it? 0 through n. Compute 0 plus 1 plus 2 plus n. That should be a 0. Now, you know, if you're a math major, there's a tricky way to do that, right? You could just do n times n plus 1 divided by 2, right? Something like that. I think that's what it is. But that's not going to help you learn how to write loops. So I advise against that solution. That is a superior solution because it saves processor time. You know, it's a formula that is only evaluated once. It's not a loop, doesn't repeat over and over again. But I want you to do it the inefficient way, just to practice learning how to write loops. So, now we want to compute this. We got to have some kind of an accumulator. So I'm going to define a variable called sum. And then we're going to have this loop, not a loop. We're going to have a loop that takes sum and it adds into sum something we're incrementing, like I. I will be 0, I will be 0, then I will be 1, then I will be 2, I will be 3, and I will go all the way up to n. And then sum is the end. Yeah. And sum contains the answer. So basically we need the easiest way to do it is with a for loop. There it is. Oh. Now on the exam, that's good enough right there.
That's good. That's not for all n.
Huh?
That's not for any n, is it? Because I can tell you n is
Yeah.
2.
This. Oh, I'm sorry. That's 100. No, I'm sorry. Thank you very much. That is not good enough for the exam. I get a B. You get the A. That's the way it works. So that's it right there. Thank you. Now, the way I stated the problem is n is an integer entered by the user. I'm not saying write code that prompts the user to type in an n and then read it into a variable. I'm saying just assume that this is done already. N is an integer that's been entered by the user. You're given n, so you don't have to write code to read it into n. And I'm not asking you to print the sum. I'm not saying to return it from a function. I'm just saying compute it. So this would have been okay for me, right, on an exam or the assignment. If Sushmita grades you, docks you for that, let me know. That's sufficient right there. And but if you want to run a test, then you'll want to test it, right? So we have to write the code for testing purposes. And let's check our work. Let's check our work. I'm a little concerned about the order of operations here because I don't want this to run first and then have a truncation happen. And if n is odd, so we really want this, and I believe it runs like that because this will be an even number, right? N plus 1 times n is even. And when we do integer division with 2, then we'll have we won't lose any information. We won't truncate. But we probably didn't have to do this because this is left to right. This multiplication and division have the same precedence, so it's left to right. That means multiplication is done first. So actually, we didn't need to do that. And just to demonstrate it, I'll do this. Okay. So 3 values, they should be identical. Let's run that. What happened? Oh, forgot a semicolon. Oh my gosh. Still a problem. I'm not even going to read that because we should be able to see the issue here. Int n, c and n, IO stream is there. Anybody see the problem?
Is it the spacing thing you're talking about the previous?
You have to close your main.
Main? You know, my ears are terrible.
Oh, on the last line with the C out, it says N instead of N.
Oh, thank you. Look at that. And the problem is they didn't put the L here. How useless the compiler is to us, really. That's the problem with C++. The compiler messages are just horrible to read. Other language is much easier. And if you're working in an IDE like Visual Studio or Xcode, they're going to highlight that for you with a red underline and say, look here. And you're going to say, oh, I missed the L. So it's a lot easier. You know, I'm doing this kind of the old-fashioned way. It's not recommended for real work, okay? All right, say 6. Ah, we got it wrong. This has got to be -1. Is that right? Is it -1? I'm guessing. I'm not even thinking about it. Here's guessing for you. Nobody caught that. Did anybody see that mistake? That should be n -1 times n. Does anyone know that? Maybe you're not. Maybe you didn't get to that in your math studies yet. That's how you compute the sum of, the first n integers.
I think it's possible.
Huh?
Because you're computing 6 plus 5 plus 4 plus 3 plus 2.
Did I do this wrong? Oh, I did do it wrong. No. That's the problem. That's the problem. Very sorry. That is the issue. Actually, that's also, not good. Yeah, so I said, did I say inclusive? The sum of integers 0 through n. It sounds like including n, right? So we should include n here. And we go back to the original formula, that's the formula that's normally, used, right? All right, so Everybody happy with that one? I think we got there. Try to keep things simple, but things are not as simple as you think. You know, look at this. Remember I talked about the order of execution? What happened if we did that? Let's suppose we did the division first. Well, it'll be okay with 6. Watch this. It'll be okay with 6 because it's even. But it'll fail for an odd number. See? Got that? That's why I, you know, hemmed and hawed over that one there. See that? Because that's why I had both of those expressions. It's important that, because the division is integer division, we need to make sure we have an even number on the left-hand side. All right. Very simple problems, but you can really find a lot to talk about in them. Write a C++ program that prints every number between 330 and 550 inclusive. When I say inclusive, I mean include 330 and include 550. Prints every number. I mean, that's pretty straightforward. Whoops, that was a mistake. Does anyone want to see that? Me do that? It's a for loop. You start at 330, end at 550. Should be less than or equal to 550. You can ask me that in the lab if you want to see that. Write a program that prompts the user to enter a number between 3 and 13, inclusive. If the user enters a number inside 3 to 12, I'm sorry, 3 to 12, not 3 to 13. If the user enters a number inside that interval, display good number, otherwise display bad number. All right, 3 to 12. Maybe I'll do it like this. So we enter the number. So here, if n is less than 3, or 2 lines like that, or n is greater than 12, then cout bad number. Else good number. Got that? That's how you do that one. It's not the only way to do it. Let's do it a different way. Let's instead of using or, let's use and. If n is greater than or equal to 3 and n is less than or equal to 12, then print good number. You see, that's the opposite. That's the other way to do it. I could use that. Logical and. That's called logical and. There's two. These are Boolean expressions. They're expressions that evaluate to true or false. They don't evaluate to a number like 4 or 6, although they actually do. They evaluate to true or false. Those are called Boolean expressions. And Boolean expressions can be combined together to form more complex Boolean expressions with the logical operators. This is the logical operator called and. And the one I showed you before was or. And then there's not. What's the not operator? Is that tilde? Hey, we never use it in this class. Oh yeah, not, that's right. It's exclamation. Sorry. And you know, we could even do it like that. If not, you know, if not n less than 3 and not, n greater than 12, if it's not the case that n is less than 3, and it's not the case that n is greater than 12, both of those conditions hold, then it's a good number. Let's see if I got it right. Whoops. And this works because this not operator has higher precedence than logical and. Maybe it doesn't. I forgot this semicolon. That's a good number, right? That's a bad number. You see, and of course this is unnecessarily complex. We could also do it like this. Oh no, that won't work. Not greater than, that means less than or equal to, doesn't it? Anyway, we're making it messy on purpose here, but I wanted to show you the not operator. All right, that's enough for that one. Oh, here. This code prints odd number when the user enters an odd number. Does not print anything when the user enters an even number. Rewrite the code so that it prints even number when the user enters an even number and does not print anything when the user enters an odd number. So this is the modulo. So you input I, so get some integer I, and divide it by 2. If you get a remainder of 1, then it's odd. So if you want to print even number for even numbers, then you just check to see if the remainder is 0. So change the 1 to a 0, and then change this word odd to even. So if I mod 2 is 0, then print even number. That's the answer for that one. And that's it. I'm going to move on. Everyone okay? Yeah.
Earlier when you had like the slashes, is that a comment? You made like a line using slashes. Is that
That's a comment. The line with all the slashes is a comment because the first 2 characters were 2 slashes. Doesn't matter what comes afterwards. They're ignored by the compiler. Huh?
Once it's built to that line, you need to watch out. If you make another line after you press enter, it actually you have to use the parameter comment, right? Because if you do // that's just for that line.
Yeah.
But if you press enter, you have to watch out.
That's right. Right.
Make sure it's
If you want a multi-line comment, that's anything that comes after here is a comment. So you could put all slashes. It was easy to hold the slash key down. If you want a multi-line comment, you want to get a block, it only comments out the line. If you want multiple lines, then you need to use */. And the closing delimiter is */. The opening delimiter is /*. And these could be anywhere. This could be, I could have it in here. Okay, tell me, what does that program print? Who can read that? Oh, that's not going to work. Did I get that wrong? No, wait a minute. This is not what I wanted. There we go. Sometimes you see people doing stuff like that. It's really hard to read, of course, but see, I commented out this block here, and I commented out this block here. So the only thing that runs is that. So sometimes when you're debugging, you comment out blocks of code. If we just wanted to run this by itself to see what it was doing, we could do a comment like that. All right, let's get low on time here. Let's go and talk about this lab on expressions. Oh, I'm sorry, algorithms. Detecting prime numbers, we did that. Listing prime numbers, I think that's not too hard. Factoring numbers. And write code that factors the number. So if the user enters in 100, the program displays 2255. Those are the prime factors of 100. If the user enters 4, program displays 2, 2. 4 is 2 times 2. 100 is 2 times 2 times 5 times 5. Then we have generating random colors. Which one do you want to look at in this lecture? I don't know if we have time for both of them. Generating random colors or factoring numbers? This is a longer program, this one here. All right. This one you can think about. This is a great, factoring numbers is a great exercise to work on. It's good for math majors. It's good for the computer science majors as well, right? So let's look at generating random colors. Write a program that generates 100 random RGB color values. So this is what an RGB color value looks like: red, green, blue. That's in hexadecimal notation. That's a number, but it uses hexadecimal digits rather than decimal digits. Decimal digits go from 0 to 9. Hexadecimal digits go from 0 to F. And F is 15, right? Just like 9 is 9. 9 is 1 less than the base, 10. F is 15, which is one less than the base, 16. It's base 16. So the output should look like this, random color values. And I have a big hint here. And we need to include seed time, probably, to seed the random number generator. Let's, how about just do it? So it's going to be a loop. I'm going to show you how to do this sequentially. One way, 100 random RGB colors, 100. So that means we're going to do something in a loop. That's going to run exactly 100 times. That's one way to start the problem. Look at this. You see, I'm stubbing out a solution. I'm building a prototype. I'm going to build a sequence of prototypes until I get to the solution that I want. So let's print 100 color values of the color white. So it's the color white. All F's is white. But this doesn't work. What did we do wrong? Oh, the same. You know what? I've never ever made this mistake before. Uh-oh, I got to retire soon. All right. So, wow, that was all that noise. There's the 100 Fs. Now, 100 is too many to look at. So we'll change that back to 100 when we're at the end. Let's just look at 2. All right, that's easier to stare at, okay? And we'll change it back to 100 at the end. See the technique I'm using? You sit in lab or at home and you start working on problems. I recommend you do this. It should be runnable very early on. You should have some partial solution very early on in the problem-solving process. That's how people normally do it. It's not always thought of as the best way to do it, but in practice, this is how people do it. All right, now what we want to do is we want these to be random strings. So this is going to be some kind of a random string here, right? So I'm going to call it color. So maybe we'll have a string called color. You know, like that. So we have a string variable called color. I'm just getting there. There we go. So in the loop, we're going to need to sort of, looks like what we do is we start with an empty string. This is what I'm thinking. We start with an empty string. And then we have another loop on the inside. We need 6. We need, is that right, 6 or 8? We need 6 or 8. We need 6 because we don't have alpha. It's just RGB. No alpha. If there's alpha, we'd have 8. So we want 6 hexadecimal digits. Right? That's 6 hexadecimal digits. You know, this is a 6. That's an A. These are hexadecimal digits. So we want a loop here that runs 6 times. And what it does is we initialize this color string to empty, and then we append onto it a randomly generated hexadecimal digit. Well, we're just going to use D for now. You see the incremental? I'm just trying to get you to go with this. We got that far. Look at that. Look at all that structure we've built right there. See, after we create a variable color which has empty length, which is empty, 0 length. We append 6 random digits, and then we print it. And then we start all over again and set it back to an empty string, generate 6 random digits, print it, and so on. We do that 100 times, because we're doing it 2 right now. So now let's get this random value here. And this is going to be, we'll do this, we're going to make it a digit, a hex digit. And we'll call that, you know what, there's so many different ways to do this. Let me do it like, how am I going to do that? I'll show you, you know, we're running out of time. I'm going to show you this way. We're going to do it like this. We're going to generate a random number n. That's between 0 and 15. Using that trick right there. And that's the hint that's given in here. Right there. If you take a random integer and you mod 16, you're going to get a value that's either 0 to 15. So that's our, we need to translate those into hex digits. So then I think the easiest way to do this is like this. If n is 0, then let's append the character 0 onto the string. See that? If n is 1, we're going to append a 1 onto the string. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that's a 2, that's up. That was not good. That's a 3, a 4, 5, 6, 7, 8, 9, a, oh, that's not going to work, 10, 11, 12, 13, losing it here, 14, 15. So we're going to append a 1 when n is 1, 2, 3, 4, 5, 6, 7, 8, 9. What do I do here? A, thank you. A, B, C, D, E, F. That's it right there. There it is. And we want 100 of these. That's 100. But look, every time I run it, like the same value, F0, 6, BD3, I get the same sequence. So it's not random enough. What do we need to do? Yeah, we got to seed the random number generator, S rand times 0. We're seeding the random number generator. Times 0 is the number of seconds from some epoch. We're going to pass that, and that's an integer. We're going to pass that integer into the srand. That's a function that seeds the random number generator. You know, if you play Minecraft, you can generate, you know, you can control the world you generate by changing the seed, the random number generator. I think, I didn't try this, but if you put the same seed in there, you get exactly the same world. Is that right? Does anyone know?
Yeah.
That works, yeah, okay. So this is like the beginning of Minecraft here. All right, we're getting started on that. So that's that's it. That's one way to do it. There's other ways, you know. I think that's a simple way to do it. But what I wanted you to get from my presentation was how I went about solving the problem. I did it incrementally, just a piece at a time. You know, I didn't see the whole solution all at once.